Good morning, everyone. My name is Michelle Patron. I'm Director for Sustainability Policy here at Microsoft, and thank you for joining us for today's at Microsoft. It's our monthly discussion where we discuss issues at the intersection of technology and policy. And with Earth Day on Saturday, and this being Earth Week, we wanted to explore the issues related to the environment and how advances in cloud-based technology are enhancing our efforts on conservation, particularly biodiversity. And so we're really excited to have an all-star panel on this today and look forward to a robust discussion. You'll see that we have a live stream, and we'll have the tweet stream going at AI for Earth throughout the discussion. So thank you for joining us once again, and let me turn it over to Brett Rose, lead engineer from ESRI, to moderate our discussion. Thank you.
Great. Hello and welcome. So yes, just to begin with, I think we'll just jump right in, or I don't really have anything prepared to say except that I'm really appreciative of all the efforts and work that you all do across the conservation space. ESRI has always been looked to this sort of space as a partnership with a variety of organizations across the federal government, but also in the NGO space and in multinational. So to get started with, I guess we'll just jump right in and talk with Dr. Alex Dehgan, right? So he was former chief scientist at the United States Agency for International Development, USAID, and is currently founding partner of Conservation X, an organization dedicated to conservation technology. So as we go forward, I'll just introduce each panelist and ask a question that we've prepared in advance, and we'll answer and maybe have a little discussion, okay? So you created this entirely new organization, right? The Conservation X, and you're dedicated to bringing conservation technology solutions to market. So can you tell us why you think technology has such a potential to revolutionize biodiversity conservation, and in particular, how you see AI being able to help accelerate our ability to succeed?
Yeah, no, absolutely, and thanks to Microsoft and to Lucas and to the team here for having us here. And I guess the first answer is, I helped set up an institution at USAID called the Global Development Lab, which was literally our DARPA for development. And I saw the fundamental changes in our ability to transform the reality of what is possible. And as a conservation biologist who spent eons in the field building national parks, creating around the world, I recognized that we weren't winning. We have had the Society for Conservation Biology for 30 plus years now. We coined 30-something years ago at the National Academy of Sciences the word biodiversity as Tom Lovejoy. But the fact is that our solutions tend to be linear and our problems are exponential. So how do we actually harness something where there is an exponential, which happens to be technology? And I saw kind of like some opportunities and some problems. The first is, I would say the problem of conservation is it's filled with conservationists. And I'm a conservationist, right? And I always like to joke, we are absolutely the most depressing people to invite to dinner, right? Like if you want to kill a dinner party, let me talk to you about extinction. I'm literally an extinction biologist. And in Madagascar, we've already lost 90% of the forest, right? I just got you guys all down. But the fact is, we saw this happening in global health. Global health used to be a field of tropical medicine. And it went from physicians, right, a single discipline field, to a field that now involves economists and technologists and engineers. And we've got to take the similar sort of approach. And we've actually made dramatic successes because of that change. I think second is that conservation historically, and this is fundamentally changing by the presence of my colleagues here, particularly also Sam from TNC, has been deeply skeptical of technology. But many of the questions we are facing now require us to harness these emerging sciences and we've got some ethical questions that conservation by itself can't answer, right? So do we use synthetic biology to allow coral reefs to actually withstand ocean acidification and warming, or do we let those reefs go? Do we use it for what we're trying to do in terms of increasing our food security around the world? Or are we going to lose the Congo Basin and the Amazon, because that's what it actually, what 9.6 billion people by 2050 means. I think third is this vast democratization of science and technology, the power of all these smartphones that everyone except for the people on the panel are allowed to have, are really sensor kits. They're platforms for allowing us to do a wide variety of things. And Lucas's former office mate during his PhD runs an organization called iNaturalist, and iNaturalist, has greatly increased our leverage and scale to do surveys around the world and track and monitor what's going on. It counts for 80% of what goes into the global biodiversity information facility run by the Smithsonian. 80% of it is coming off of this app, and in fact, it is probably the best data that they're getting it. And then finally, I think we can greatly increase our reach by using tools like AI, and I can talk perhaps later, because I don't want to go on at length, about what we're doing with the Department of Interior and what we're doing with a series of others, just because people believe things like the Invasive Species Challenge is unsolvable, when in fact, if we've got the technology to put this Volkswagen-sized rover on the surface of the moon, we've got the ability to actually address invasive species, and particularly where AI can increase our reach and our strength. And then there's just technologies that are currently on the horizon that give us unprecedented ability to improve the resilience of our systems, to restore our systems, to be able to actually come up with replacements for these underlying drivers of extinction. So I'm incredibly hopeful, and we can get more into AI specifics, but that's kind of the reason why I thought it was worthwhile to have an organization that can help both source these types of innovations, create a platform, which is one of the things we're doing, digital makerspace, to help other people help us co-create these solutions, and then the keys to bring them to scale.
So fundamentally, human capacity to create technology to solve unsolvable problems is something that's been repeated in history.
Absolutely.
And you're just going to repeat it again.
There's a pathway there.
Great, okay. So our next panelist is Dunn, who's president and CEO of the Chesapeake Conservancy. He's the founder as well, and Chesapeake Conservancy, for those of you who haven't heard of it, is an organization that's dedicated to preserving the Chesapeake watershed. So as the founder of the Chesapeake Conservancy, you have positioned your organization as a leading proponent for a new idea called precision conservation. And can you explain a little bit about what that means to you, and how technology like AI is being fit into that vision for the Chesapeake Conservancy?
Sure, and thank you so much, Brett, for moderating. Thank you, Microsoft, for having us. Just a note of clarification, I didn't found the Chesapeake Conservancy. I was there at the beginning, but my mentor, Pat Noonan, was actually the one who founded the Chesapeake Conservancy. He actually founded the Conservation Fund and a number of other major institutions in the country. So I was hired as a CEO of a very small nonprofit to make a difference in the Chesapeake. I love the Chesapeake Bay. I live in the Chesapeake Bay. My family lives there. I'm trying to save the places in the Chesapeake that matter most to our community. And, when I was hired for this job, we were expected to make parks and refuges and trails and a very traditional sort of conservation approach, much like Alex sort of made reference to. And we've done that. We've made national parks, and we've expanded national wildlife refuges, and we created a national trail, the John Smith National Historic Trail in the Chesapeake. And those are great things, and they are symbols of progress for our Chesapeake Bay. But our Chesapeake is still struggling, although there's been some good progress lately with water quality and grasses. We still have a very, very threatened ecosystem, and those threats aren't going away. And so we needed to think differently about how we were approaching conservation in the Chesapeake. I was not satisfied with the traditional approach, and I'm actually a fairly rebellious person, and I question authority a lot. And one of the things that I asked was, could we do this differently? Could we leverage technology to actually take this movement to the next level? And so I had a very supportive board, and we founded a program called the Conservation Innovation Center, and I hired some really talented staff, two of which are here today, Jeff Allenby and Cass Pillai. And I challenged them. I said, look, what is the fundamental unit that we're missing in the Chesapeake Bay? And they came back to me and they said, look, land cover data is really lousy in the Chesapeake. We have 30 by 30 meter land cover data. It's 5 to 7 years old, so we're slow. We don't have the information, the parcel scale data we need, and you know, we're behind the ball. And so I challenged them to come up with a new way to do it. Come up with better high resolution land cover data. And they did. And when they did it for a county, I said, can you do it for the Delmarva Peninsula? And they did. I said, can you do it for the whole Chesapeake Bay? And they did. And so we now have produced high resolution land cover data for the entire Chesapeake Bay watershed, 1 meter by 1 meter resolution data. We did it cheaply, we did it fast, we did it with ESRI's technology, we used Microsoft's cloud-based servers, or Azure servers, and Intel gave us the grant that we needed in order to do it. And so then we approached the White House with this data set that we worked on with the Chesapeake Bay program, the Environmental Protection Agency, and the National Park Service. We said, look what we did here. This will make everybody faster, smarter, more efficient, more effective. We'll operationalize ecosystem markets. We'll make us better and get us ahead of the ball. And the White House said, that's great. Can you do it faster and cheaper and for the whole country? And so then we said, okay, let's integrate artificial intelligence into this. Rather than manually doing this, which we did the first round, let's try and automate the system. And so I challenged my team again. I said, okay, can you do this with artificial intelligence? And they trained the system how to train itself. And so now we're approaching this very differently and at a much larger scale. I think this application could go national, could go global, and could really arm little local governments, nonprofits, federal agencies around the world with the information they need in order to be more efficient and more effective. And what we've done, I think, is, I call it our Kitty Hawk moment. You know, it was 30 seconds of flight, if you will. And you know, when the Wright brothers did that, it took 5 years before the New York Times actually wrote about it. So I think what we've done in the Chesapeake, it's our Kitty Hawk moment. I really think it has dramatic ramifications for the conservation movement around the world. So if you're talking about rainforest deforestation or the loss of reefs or the melting of glaciers, you know, all of this, the applications we've pioneered here in the Chesapeake, I believe have direct relevance to those challenges around the world. And here's my sort of pitch to this community is that we can't do it without the corporate world, without the corporate tech world in particular. If we want to save the planet, we need engagement from corporations like Microsoft and Intel and ESRI on a scale and in a way like never before. You know, we saw that the Trump administration's budget was released recently, and programs like the Chesapeake Bay were slated for elimination. I mean, that is a direct challenge to us in so many ways, and what we need is to step up as a community, not just the nonprofits, but the corporate world, and partner together to solve these problems. We've proven we have the technology and the technique to do it. We just need to scale it up, and we need to apply it and integrate it into the fabric of our decision-making processes in our society. I feel really confident that we have something to share with the community, and we're making really good progress in this regard. I want the Rockefellers and Mellons of our day, the owners of those technology companies, to join us in this effort to save this planet. And today's panel is a great opportunity for the conservation community to convey to them how their technology and their resources and knowledge and talent can be applied in a way to conservation like never before.
Wow, that's great. Yeah, I share your sentiment. I think ESRI is fully on board with conservation as a goal of our technology, and I think we always have been and have proven that time and time again.
Absolutely.
So thank you for your. So next on our panel is the gentleman who actually kind of helped put this all together, and that's Lucas Joppa, who is Microsoft's chief environmental scientist. That's all I have for your vita there. But enough said, right?
I'm in stealth mode.
Yeah, exactly. So obviously, Microsoft understands the power of AI. You guys have a great platform for it. The news has been filled with all kinds of stories about how your AI product releases and investments have really helped change a lot of different business practices. So as Microsoft's chief environmental scientist, you sit at an interesting place where AI as a business tool can also be used to meet the needs and deliver the environmental sustainability solutions as well. So but also for the company's operational work as well, not just for reaching out to businesses. So, so what is Microsoft's really position on how those two aspects of your job come together?
Sure. So I think the answer for me, at least, is pretty straightforward. So what's clear inside the technology industry and inside Microsoft is that the world's undergoing a new technology revolution, and that in large part, that revolution is going to be powered by significant advances in artificial intelligence. For us, that's a huge opportunity. It's at the scale of our previous ambitions to put a computer on every desk and in every home. A goal that we set for ourselves that really ended up fundamentally changing the infrastructure of a lot of today's social and economic systems, for instance. We've got a lot riding on this. As you mentioned, our investments in this space are not trivial. And our perspective on it really is, to use the word that we've already heard today, is to democratize AI. So what we're really looking to do is to take the artificial intelligence solutions, the services that a Microsoft can run internally, that a Microsoft can infuse into our everyday operations, democratize that and put that out into the hands of people all around the world. So we're already doing that, right? I mean, you can, with the click of a button, you can access over 20 algorithms already through our cognitive services marketplace, where you can get access to applications like speech and image recognition that are already at the same skill or better than human levels of cognition. And then we're infusing that in a lot of our popular products, right? So there's people all around the world today, probably right now, using our real-time language translation services in Skype, for instance, right? And that's all being powered by these decades of research and investment that we've put into artificial intelligence. And so from a business perspective on AI, that's all good, right? The news is good. But it's really clear that we're also doing business at a pretty unprecedented time in human history, right? Human societies are being faced with this challenge of mitigating, adapting to changing climates, ensuring resilient water supplies, sustainably feeding a growing population our population growing rapidly to 10 billion people, all while trying to stem this catastrophic loss of biodiversity, right? And the numbers there are kind of crazy. So my academic specialty is I'm an extinction biologist as well, and my colleagues and I have written numerous papers showing, right, that extinction rates are over 1,000 times higher than you'd expect in the absence of human activities. And that loss is already having serious implications on the decay of important ecosystem services like pollination that, whether you like it or not, we all rely on every day. And so some of those issues, right, directly affect our operations, like you mentioned. All of them directly affect our global ecosystem of customers and partners, and they really support and drive most of the world's major economic markets. And so it's because of that that we're pretty convinced that ultimately in the long term, the future success of our business, of communities, and of the global economy is really going to be dictated by our ability to leverage the artificial intelligence successes and technologies of this new industrial revolution to counter these really complex environmental challenges. And so that's really kind of that's the motivation for my job, is figuring out, helping the company figure out how we democratize our AI tech so that people on the front lines of conservation biology, to Alex's point, aren't necessarily technologists, how people on the front lines of conservation biology and other environmental topics are able to not only have access to the relevant AI tech that's out there now, because access is a big and important topic, but also has the education and the knowledge about how they can apply today's technology and the technology that'll be coming ever more rapidly down the pipeline into the future to their problems, and have the knowledge and the ability to be able to actually implement those solutions. And it's that gap that's really kind of top of mind for me today on this panel. I think we've already heard from two, my co-panelists, we hear for two more, and I think and I know everybody up here, so I know this already, and I'll just tell you, they're all exceptional. And in many good ways, but one of the ways that they're exceptional is one that really worries me, in that what you're looking at here doesn't represent your average conservation biologist, right? And so one of the reasons I was excited to be on this panel, help put it together and have this conversation with the audience, both here today as well as hopefully extended after the panel, is to think, how do we turn your average conservation biologist into somebody that looks a lot more like and is able to speak and act a lot more in the ways that you'll hear today. And so I'm in the very early stages of my thinking here. As a company, we're starting to put our brain power on this topic, but just selfishly getting the input of the panelists as well as the audience today is going to be hugely helpful for me.
All right, great, thank you. And it's a very exciting time to see how the burgeoning technology that we have in the cloud with Azure and other platforms is really helping to push down to that last tactical mile or usable mile that these kinds of techniques and procedures that have typically been in the hands of some elite data scientists maybe. So it's really exciting. So next on our panel is Sankar. He's speaking of 4 standard deviations from the average conservation. Sam is a senior advisor for the conservation technology at the Nature Conservancy. He's an environmental lawyer, engineer, and executive, and he joined the Nature Conservancy to accelerate the use of technology for conservation purposes. So that's why he's here. So Sam, you're in a very unique position as a former engineer, lawyer, and executive, now tasked with advising one of the world's largest environmental nonprofits on how to integrate technology to scale up their impact, primarily, right? And from that perspective, we would really like to hear your opinions on what role big environmental NGOs should be playing in this space, and what challenges you think they might encounter.
Sure. Well, first of all, I should thank Microsoft for having all of us up here. I think it's a very timely and important discussion. I think it's worth saying, I started out my career as an environmental engineer in the early 90s doing work on Superfund, which seemed like the major environmental issue of the day. I decided that the law was really the place to go to make bigger impact. I went to the Justice Department and worked as an environmental lawyer for a while. And then I realized that actually the corporate world was going to be someplace that really had a lot to do, because suing corporations was not necessarily the best way to get things done. I went to General Electric, where I was an executive for years in the environmental world. But there I saw that the technological revolution that was happening inside of GE, that Jeff and others were bringing along, was really reshaping the industrial world. And I went to Mark Tursick, the CEO of the Nature Conservancy, and I said, "What are you doing?" And he said, "Not enough. Come help." So I joined the Nature Conservancy about 7 months ago on the mission to bring the world's largest, most successful, as I think Alex or Joel said, in their words, the most successful environmental organization, 3,500 people, which to me seems pretty small because GE had 350,000 people and the federal government had a lot more even than that. So how can big organizations in the environmental movement help? The first thing is by reshaping themselves, I would say. That, as I think Alex said, there's a lot of conservation biologists out there. The movement was started largely by folks who had a biology background, who were very interested in the critters and the plants that were out there and how they could help at a very granular level. And as Alex again said, the problems are scaling exponentially. We have linear solutions. So what are we going to do to move along faster? Well, if you're a big NGO, you have a bunch of behaviors, a bunch of set assumptions about how not just to do your work, but how to raise money for doing your work, how to staff up your teams, who to bring in, how to set your strategies. So as the Conservancy evolves and looks to go faster, it has to confront, just like every other environmental group is now having to confront, how do we as an organization become faster and more nimble. You look at tech startups, they work on cycles of weeks and months. Funding cycles in most NGOs take 6 months to a year or even longer for AID. So how do you accelerate those curves and those paces to work better? Well, my advice is basically don't wait. Don't wait. Speed doesn't happen through plans. Google famously, not to mention another large tech company in the world, but famously doesn't plan more than 6 months in advance because it just isn't worth it. So the Conservancy, I'm going to talk about one specific project we've got involving tuna in the Western and Central Pacific, jumped in, and a small group of folks from our California chapter decided to get involved using AI to help conserve tuna. In the Western Central Pacific Ocean, there are 8 nations that control 60% of the world's tuna fisheries. A $7 billion fishery controlled by 8 small nations. The advantage that someplace like the Nature Conservancy has is that we have long-standing relationships with these folks. We're able to work with them and to address a major problem they have, which is a lack of monitoring of their fisheries. They have 98% of their vessels are unmonitored. 98% are unmonitored. The vast majority of their economies depend on this. And an important fact about a lot of these fishing situations is that it's mostly licensed boats that are doing the illegal or unreported fishing. These are boats that have licenses but are maybe taking more than they should or unknowingly taking bycatch. 30% of the catch in this area is unintended. So how do you monitor it? Well, we put in a system, artificial intelligence-based computer vision system that's starting to recognize what fish are being caught overboard or caught above the rail. The thing that the Conservancy recognized is that we were not going to hire a whole ton of data scientists and artificial intelligence experts. We needed a critical mass of people who understood how to move data, how to work with outside technological experts, and how to do the basic infrastructural work to assemble that data in one place. But then we crowdsourced it. We sent out a challenge, a $150,000 challenge on Kaggle. We got 2,000 submissions of algorithms back to analyze the video. We were hoping for like 100. 2,000 submissions. But even more importantly, we got the technology world engaged. We had people coming out of the woodwork calling us up going, you're thinking about this all wrong. This is the way you ought to be doing it. And it turned out that one of those companies, which wasn't even really an image recognition company, has partnered with us. And we're really moving forward with them because they said, think about it differently. And the big success was when some of the commercial monitoring companies came to us and said, hey, we weren't really on board early on, but we get it. We see what's happening, and if we don't get on board with this independently for commercial reasons, we're going to be left out. So that's a great success when a big organization leverages its relationships, gets small, gets started, and makes an impact.
Wow, great. Yeah. I know it's always important for every large organization to think about how they're going to pivot or maybe reinvent themselves. And so I guess that's one core part of the Nature Conservancy. Good to hear. So our final panelist, but not least, of course, is Professor Tanya Berger-Wolf. So she's full professor in computer science department at the University of Illinois in Chicago, and a founder of the organization Wildbook. And it's a nonprofit that uses AI to identify species and individuals in photographs and data to support wildlife research and conservation. It's a great app, which we'll see later. So Tanya, you are a classically trained computer scientist, so I think you're the only one, perhaps in this room, who's a computer scientist. Great, it's good to have you here. And now a full professor in a top computer science department, and you spend much of your time researching how AI can help monitor wildlife populations. So both their abundance and as well as their behavior can be sort of captured in a Wildbook. So can you explore or explain, how basic AI research and wildlife conservation complement each other and the opportunities and challenges for academic community to become more engaged in this community?
Yes, again, thank you for having me here. And I'm actually a little bit sad that I'm the only computer scientist in the panel, and I think the point of this panel and events like this is to make sure that I'm not unique. Hopefully, that's what comes out of it, because I think the biggest challenge is the translation challenge. And Lucas, you pointed out that you see your job as sort of translating between the technology for conservation biologists. I see my job as translating the other way around, from questions that come up in conservation biology and more broadly in ecology and biology for computer science, to extract the computational challenges from that. Because as you pointed out, that engineers work on challenge. When we see a problem, we see a question, and our response, 90% of the time, oh, I can do better. Right? And it's that what drives us, and it's that what actually brought me in the first place to this space of wildlife biology and conservation. So I am a classically trained computer scientist. By inclination, I think algorithmically. I think by training, I think algorithmically. Not after my PhD. Not until after my PhD, I even came to ecology as the source of questions and challenges. But when I did, it did come from seeing the way questions were asked and problems were solved, and thinking I can do better. There's a different way of doing it. And not only it sort of solves one unique puzzle and I can help answer the question, but it led me to see that computation in general can play a huge role in this process of sort of seeing the wildlife and the big world and all the biodiversity in it, from data to analysis to sort of hypothesis generation and supporting policy. Because at every stage of the way, it expands the sort of data, the lens through which we look at the world. And we saw ESRI, and we saw the sort of every solution here, it essentially expands the basis, the data, the type of data, and the amount of data. But once you have this very different lens through which you look at the world, you can ask different questions, and you have to answer these questions differently. And for that, quite often, turns out that the computational solutions do not exist. And they have to be computational, not only because of the amount of data, but because humans actually suck at seeing patterns in large amounts of data. Because we're hardwired to see certain patterns. We see faces in all random collections of points. We overestimate the outliers. We don't see patterns that span large amounts of time or space. So we're really not good at that. We need artificial intelligence. We truly need computational solutions to extract the patterns from all this massive data and bring it together in a way which is very different from the type of approach and the type of sort of biological quest for understanding data that looks for explanatory models, that looks for sort of mechanistic explanations of what's going on. Because artificial intelligence solutions, machine learning solutions produce models that are not explanatory. So it's a shift in the way we understand data. Right? It's predictive. It's actionable. It's descriptive. But we can't explain, what are the biological processes behind it quite often. So there is the translation that has to happen both ways for this to be really useful both ways. We both need, and all of you are great examples of coming from the conservation biologist side, from biological side of understanding what technology can bring, but we also need to translate it the other way around and sort of take that challenge in conservation for computer scientists and to show that there is a challenge, that the questions are not being answered, And the solutions that are created for different space not always can translate directly into the space of wildlife biology and conservation. So, which is great. So my collaborators in conservation biology, in biology in general, get very, very sort of anxious when I say, oh, this is great, because they know that, because they know that that means that the solution doesn't exist, that it's a computer science research problem, and that they will have to wait for it for a while. Yeah. So, but being in academia, right, it is, our product is research. It's research papers. It's solving new problems. If the solution exists, I can give it to you and, you know, here it is, go. And if you're a biologist who is educated to understand what the solution means, or you have Lucas who knows how to translate it, or anybody else, then my job is done. And I'm hoping that most of the questions that I would be getting will be of that kind, that, oh, here's the answer. Here it is, off the shelf, and we can sort of create a solution. But it's not. It's a nascent space where the most of the questions that are coming are still not, the solutions do not exist. And while I'm excited to create these solutions, I found out that my job cannot end with publishing a research paper in this space. So one of these questions, majority of my research is working with biologists who are interested in social behavior of animals. And so the types of algorithms that I create most of the time is for understanding dynamic social networks. And at the level of abstraction, it doesn't matter whether it's zebras or baboons or humans or brain cells for that matter. The biggest difference with animals is that they don't have Facebooks. So how do you get information on animals of where they go, how many of them are? So it turns out, and to my shock, that for most of the species, we don't even know how many animals there are. We don't know where they go. We don't know who they're with. This is basic data for research and for conservation. You don't know how the numbers change year to year or region to region. And animals are not interested in political borders, so we need to do it at scale. We need to do it all the time, right? You cannot have one individual walking around following a group of zebras. That's not going to give you the right numbers. So you need to have a solution which can watch all the animals all the time, ideally, right, everywhere. So, you know, it started with zebras. Zebras are walking barcodes, or fingerprints, actually. So it was a class project to create a program that can identify individual zebras from photographs. But then another engineer heard about it and said, we can do better. The classic engineering approach, right? Computer scientist, computer vision specialist, Chuck Stewart at Rensselaer Polytechnic Institute. And so we scaled it to build a system which can take now hundreds of thousands of images, and we can pull out the images automatically using computer vision, using AI approaches of a given species, and not only tell you, oh, this is a zebra, this is a giraffe, and this is a turtle or a whale, but this is Zipper the zebra and Joe the giraffe. We can recognize individuals and, you know, Willie the whale and Terry the turtle. And together with the information on when and where the image was taken, you can now track an individual, you can count them, you can know where they're going and who they're with. And so, for example, and you can scale it up. You can now crowdsource that information. Just like you did with tuna, we can do it with zebras and whales. So a year ago, we did the first ever full census of an entire species, the Grevy's zebra, 95% of whom are in Kenya and they're endangered, using people just driving around for 2 days all over the country, taking pictures. And this is from local school kids to U.S. ambassador to Kenya, Bob Godek at the time. More than 40,000 images of zebras. We identified them and counted all of them, and that's the official number today that IUCN uses for the Grevy zebras. That's the most accurate count. So that's what technology can bring. And we can do it for any striped, spotted, wrinkled, notched, or uniquely identifiable species. We partnered up now with World Wildlife Fund to build wild books for soul-ringed seals in Finland, and for Iberian lynx, and for and the Internet of Turtles, the other IoT, for all the sea turtle species. So the translation that happens both ways and goes from, you know, a little research paper that's published has to be then brought back to this community. And to me, seeing both ways, solving the exciting challenge in computer science, but then seeing the impact that it creates in real world is amazing.
Right. Yeah, I definitely agree that it's really exciting to see seminal, interesting work where academic folks put together different techniques and technologies and create create unique solutions, be adopted by other entities that can really democratize that sort of technology and technique across various spaces. That's really great stuff. So with that, I mean, I think that was been a pretty robust introduction to the panel and the work that all of us do up here. And so now we'll use some time to actually answer questions directly from the audience, unscripted. Yes. So I think we have hand mics. So yeah.
So I have sort of a two-part question. Seems like a lot of this is based around image recognition and sort of, or the examples that I've heard. Is there any way that you could explain that, how that technology works in a way that I might understand it? And a follow-up, what are the things coming down the pike in the next several years that you guys are excited about that you can apply to your challenges?
Maybe you have
am
a
I the
simple
one?
explanation of how AI can do image identification?
Right. So there's a great XKCD cartoon of can you build an app of finding the location of a bird at any given point? Yeah, sure. You know, or you know, I would just take the GPS of an image and that's all in the image data, and then I can pull out that location. Well, can you identify the species? Oh no, they'll give me a grant in about 5 years. so that's the tough problem. There are roughly two parts to sort of the computer vision work that's going on in this space. One part of it is finding the object of interest in the image itself. So that's the detection part. And a lot of these deep learning techniques that we're hearing, that they play the sort of the central role in that process. I mean, okay, so to back up, the entire computer vision, the way it works is all you have is pixel values, right? And you have to take these pixel values and translate them into some objects that we're talking about. And all the techniques that work in computer vision, they essentially translate functions on pixel values into some higher level functions that we call features that then somehow relate. When you give enough example, this is a zebra, this is a zebra, this is a zebra, this is a zebra, this is not, this is not. They gradually learn to create these higher level functions from pixel values that recognize, that correlate really to all the zebras versus separate them from the ones that are not zebras. That's at a very high level. Yeah.
I was just going to chime in on the land cover. I've got a little more basic description of how it works. I try and think of it how I would explain it to my mom. And so what I say is basically we take aerial images, like the National Agricultural Imagery Program takes pictures of every square inch of the United States every 2 years. And you as a human can understand that's a tree and that's a road and that's a field, but the computer doesn't necessarily know that. So what we do is we tell it what it's seeing. We say that's a tree, that's a road, that's a field. And we turn that picture into ones and zeros so that we can do math on that image. And then the power of that is, in terms of landscape scale conservation, is you can do extremely complex calculations on areas from Cooperstown, New York to Virginia Beach, Virginia, like in the Chesapeake here, in a way we've never been able to comprehend before. The human mind can't necessarily think about, okay, where should we do a restoration or conservation project across that vast landscape? But because we've translated that landscape to ones and zeros, we can build an algorithm and calculate, do some calculations and identify where the priority areas are. So I know that's a very basic description of sort of AI and land cover, but for me it works because you're taking a photo and translating it to ones and zeros, and hope that helps.
If anybody tells you that they know exactly how this
Yeah,
is working, and they're not a computer scientist who spends their time immersed in this, they're probably hopelessly out of date. Some of the best information we get is actually, some of the most valuable tech partnerships we have are from individuals from companies like Microsoft who work closely with us just to inform us. There's a guy named Arul Menzies who's out in Washington State. I sat down with him to talk about our tuna project. He said, this is what I think you're going to need to do. You're going to need a ton of data. You're going to need this. He called me up that afternoon. He said, and this is a guy who is a deep learning expert from Microsoft who does language. He called me up that afternoon. He said, I'm totally out of date. What I told you was from 7 months ago. And it's totally out of date. I was wrong. Here's what you need to be looking at. And that's when you say, as an environmental organization, whoa, we better crowdsource. We better get out there. But the second part of your, the second part of your question, I'm just going to give you a couple of things I'm excited about. Blockchain for supply chain tracing, I think is going to be very interesting for things like fisheries and timber products. A lot of companies like GE are already following that very, very closely for their own reasons. Another one is in situ sensing for water quality and water volume. Distributed sensing, interconnected sensing, you're going to learn a lot on the ground about that. Oh, I got so many. Social information data mining, the way people's habits influence the environment. There's a ton of information on what they're doing every day. Boy, I could just go on. I think
Crowdsourcing?
So yeah, the second part is there's all these techniques that the tech world is bringing to conservation, just things like crowdsourcing that are real new.
Well, it's beyond technique because actually AI plays a role in taking crowdsourced information and extracting actual knowledge out of it. So you really, you translate it into, you take the crowdsourced information and it's not ones and zeros of the image, but it's ones and zeros of the type of features of that information, of the properties of that information. Yeah.
Yeah, so I was just I'll answer both those questions a little bit off the back of some of the stuff I think. And for me, what I come down to, I'll give you a little bit of a technical explanation of how some of this stuff works, but ultimately nobody actually knows, even the people who build it. So if you go one level down, once I train one of these algorithms, et cetera, we still lack the fundamental ability to understand what's going on. So one of the big debates that's raging right now in kind of the deep learning community and just the statistics community writ large is model interpretability a myth, right? Or is it broken, right? Do we need to be able to interpret these models anymore? And that's a huge debate between the machine learning and AI community and kind of the traditional hypothesis-driven scientific community, and it's a hugely interesting one. But at some level, we know how they work, but really what these models do is that we've tried to build them in the same way that we think the human brain works, in the sense that, don't forget, your brain is still the most, powerful computational engine on the planet, and it's also one of the biggest data collection engines on the planet, right? So the brain looks at an image of land cover or of a zebra, and it says zebra. Why? Because society, your mom and dad, reading, everything have told you that's a zebra and that's not a zebra, or that's a tree and that's not a tree. And so we need to be able to have that much data, your X number of years of data collection and training your systems. We need that amount of data to be able to train our systems. And that's one of the bigger problems with environmental applications of AI, and it's one of the breakthrough. Each of the organizations up here has come across some breakthrough in their ability to collect that amount of data, right? So there's crowdsourcing, there's citizen science, there's getting technology to build the first map in one place, and then using the data that came out of that map to train up algorithms that are then able to do it more places, and using that to train up and train up and train up. But it requires this sustained thinking along the technology pipeline, right? Of how do you collect some data, exponentiate those data to something else, and then keep doing that and keep doing that until eventually you have a high-resolution land cover map of the US that started with some small component of the Chesapeake. And then just really quickly, how these things work. They just look at pixels and they say, what color is that pixel? What color are the pixels next to it? What color are the pixels next to the ones that are next to it? What happens if I flip that upside down? What happens if I shift it 90 degrees? Just think of all the different ways that you could mess around with a photo. And that's all a computer's really doing, is it's messing around until eventually it stumbles upon something. And so that's kind of the brilliance of a lot of computers coming together, for instance, in the cloud, right? Is you can just crunch away until you eventually learn some things about something that's really useful.
Here's a short list of stuff I'm excited about and that we're actually thinking about that I think is really cool. And I think where it is where the software is actually combining of new sensors. And by sensors, I mean everything from the cell phone in your pocket to 200-gram packs that can go on the back of an insect, which places have actually developed, to drones and UAVs, to actually nanosatellites like the 149 that Planet Labs just put into space with the last 88. So thinking about the future of camera traps. So like camera trap technology when I was a biologist was like film. Like you would set up your camera traps, you didn't even know if they were working till you'd look at the pictures, and half of them are some dude that's like looking in trying to see what is actually right there, right? But to actually where you have networked and AI camera traps, and there are multiple groups. CI is working on this, Roland K's NC State is looking at this, and a bunch of others. How do we do fish surveys and fish diversity surveys automatically using UAVs and actually doing fish counts, at a scale and precedence and terrain that we could never ever get to before? How do we do disease surveillance coupled with sensors? So we've been working on a way to do handheld identification of chytrid, non-invasive identification of chytrid in the field using Blu-ray lasers that creates a fluorescence. Because chytrid, you can't see it on the surface. It's a disease, it's a fungus, it's wiping out all the amphibians around the world. But if you can actually create fluorescence, you can map the extent of the disease. How do you automate that? How do we address invasive species for early detection and rapid response? And Conservation Metrics is using AI and imaging to look at the detection of the brown tree snake. You've got the Australians that have Hotspot, which is the robot that actually goes, looks for crown of thorns, invasive starfish, and then injects it with a poison. Like, how awesome is that? And then we've got great tools like Global Forest Watch, being able to do change detection and classification with that. But our satellite capabilities are able to now sort of go shallow penetration into water, and actually then thinking about what Global Coral Watch looks like, and how do we actually look at these things. And just giving you one idea, Cynthia Rosenzweig did a study of like 20,000 different processes that are changing under climate change. And 90% of them were found to actually be biological and physical changing. So there is no single way for any biologist or university to actually track all that. So being able to scale up our ability to understand the changes and the reorganization of our planet, I think, is spectacular. The other technology that I'm super excited about is synthetic biology, our ability to use CRISPR and something called gene drives to actually extinct diseases off the face of our planet, like white nose, like chytrid, that are driving species extinct. So we can actually stop the extinction process of some of these species that are pathogen-borne.
Can I just layer one thing on top of all of those comments? The thing that I think is most exciting about everything everyone said is we're moving from really an effort-based movement to a results-oriented movement, much more results-oriented. And that's a big deal, because we all have this goodwill. We want to save the planet. E.O. Wilson is our inspiration for wanting to save species, and Jane Goodall is our inspiration for wanting to save all kinds of creatures. But what we have here is we have the next generation of conservation, and it's a big deal that it's making this shift from effort to results. And I wanted to mention that because I think in everybody's comment you could see that pattern.
So,
And So just one shout out on the computational side. There's now a network of researchers, mostly AI, for computational sustainability, and a lot of the research beyond computer vision, but from sensors and from to anti-poaching strategies, to sort of looking at everything from rainfall and water cover to, as I said, to anti-poaching strategies and different kinds of conservation. There's a big research effort that's now complementing all of this.
A lot of amazing ideas on what's really exciting next. My one thing that I would say from my perspective, I agree with everybody, but I think one of the key things, especially from maybe a large organization standpoint, whether it's federal, NGO, or commercial, is I think we saw over the last 7 or 10 years open data as being instrumental in a variety of ways and impactful in a variety of ways, a spectrum of ways. I think the one thing that will be next, especially when we consider how difficult it is to have open big data, is open compute as a service, right? So that's that would be one thing I would really hope that the more research in. How does an organization like NASA give access to perform analysis on their petabytes of data? That's just my thing. So with that, I think we had this gentleman here. He had a question, and then we'll move on to a couple other questions.
Thank you so much. Fascinating discussion. I'm Johan Berger-Wolf with Vulcan. Joel, I think I'm going to follow up on your latest remarks there. You said effort-based to results-based movement. That's really interesting to hear. How do we make money off of this? How do we, so we can scale, so that we can actually get to the customers, the people who need to use this stuff? Thank you.
I love that question. I mean, so I think there's this huge emerging phenomenon in conservation with private capital. And so in the Chesapeake here, we've been exploring the idea of ecosystem markets with whether it's wetland banking, nutrient banking, and I think that a friend of mine, Nick Dilk, started this company, Ecosystem Investment Partners, and he's accumulated a large amount of capital to implement conservation and restoration projects that actually bring a return to his investors and make the world a better place. I think there's a scalability in partnering with private equity and firms to scale up conservation in new ways that are non-traditional. The other thing is to democratize the data, make it open data, which we did in the Chesapeake Bay, giving everybody access to this information, allowing them to innovate too. Innovation can and should pervade every organization, every corporation, every government agency, and we should fuel that innovation and encourage that innovation. So we need to think differently both about who's using it, the markets where it's being used, and how we make it available to people.
Yeah, I would just jump on there and say, you know, from a technology perspective, what AI and kind of that full applications, algorithms, and infrastructure underlying stack can contribute, hopefully, is a fundamental shift in our understanding of what is where, how much is there, and how fast is it changing, right? Your question is, well, how do we make money off of that? My response is, it's really hard to make any money in any system that when you don't understand what is where, how much is there, and how fast is it changing, right? So I try and keep my eye both on the horse and the cart, right? And make sure that they, at the very least, remain attached. And so from technology's ability to start to deliver those data in higher spatial and temporal resolutions, I worry less, quite frankly, about how money's going to get made. The markets are already ahead of the data's ability, right? So the old markets and the new, the offsets, the mitigation banks, these things are coming up and offering services and are data deficient and insight deficient at the moment. And one of the feedbacks that you hear quite often is investor uncertainty around, well, that's great, I love your product, but how do we know the result? How do we know that we're getting what we're buying? How do we know it has the impact that drove our initial investment, right? And that's why everything from land cover mapping to wildlife populations or anything else, to be able to track it gives those markets much more certainty, and that allows investment to flow.
I'm going to give a slightly contrary view to this, I think. And maybe it's from my time at an industrial multinational and as a lawyer. Look, at the end of the day, there are a lot of externalities in human behavior that have not been internalized. The economies don't properly reflect what's going on here. We all know that climate change and carbon emissions would not be an issue if we had a proper price on carbon around the planet. So that's why I think one of the important roles for people in the technology world and the artificial intelligence world is to start understanding how human behavior and human beliefs are influenced by information. Because if people in the world understood more clearly what was, in a sense, going on and what their impacts were, policy would change. And if policy would change, a lot of this stuff, a lot of the science that we do would be attached very clearly to monetary outcomes. So that's my plug for social mining, social data mining, and trying to learn how people change their minds about the environment.
I just want to jump in on this because we've got a paper coming out in a journal called MIT Innovations in June that is this question of scaling and conservation. And we're also both, we recognize, and I recognize that sourcing innovations and even piloting innovations is not enough if you don't bring it to scale. iNaturalist is clearly something that has been a tool that's gone to scale. Wildbook, it is fantastic to see it spread. And if you think about it, right, scaling in social enterprise is really hard. And there's three models that we can look at. One is digital technologies has its own capabilities and ability to scale because it is the cost of replications are low. The second is really where you're opening up a technology, whether it's hardware or software, for the community to build on. But that doesn't always necessarily get to scale. And so the third is really this question of, is there a profit model? Is there what I call dual use, but not in the non-proliferation sense, but are there secondary markets that can serve? So as we're thinking about detecting chytrid in frogs, there's not a big frog market out there, right? But in fact, aflatoxins, which affect stored foods, is a billion-dollar market. Rusts, which affect wheat and rice, are billion-dollar markets. How do we leverage one market to think about the other? And that really gets at this idea of the value proposition, and thinking about design characteristics, thinking about the business model, thinking about ultimately who's paying the cost that'd be able to do it. And one great example for you guys to look up is Recycle Bank and Ron Gonen, who recognized how to use a for-profit system to bring New York City area recycling institutions from 20% to 80% by paying people, because you recognize we were still paying for the recycling because we would have to pay for the cost of the garbage.
Great. I think we have time for one more question. Yeah, one more question.
Hi, I'm Steve Jackson. I'm with the American Academy of Actuaries. A slightly strange place to be here, but actuaries are very deeply concerned with the environment, climate change. Launched the Actuaries Climate Index this year, which measures extreme events a little more carefully than other people have a climate risk index coming out later this year that monetizes those risks against a base period. I have a simple question that I want to make a little more complicated. The simple question is, haven't heard any mention of government policies, laws, rules, regulations, other than the cut in funding for the Chesapeake. But I'm wondering if there are changes that are needed. I want to make it a little more complicated by going back to Lucas's comment about the issue of interpretability of the models. And I'm informed there by one of the main issues actuaries are dealing with right now is big data, okay? And the reason is more and more insurance companies using big data to set policies. The state insurance commissioners who have to regulate those have no idea what's going on with big data, right? And so the state insurance commissioners have just set up a task force on big data to try and figure out what it is and how they can understand it. And we've set up a task force to help them with that. So with that in mind, it seems to me, especially if there are changes needed in government policy, I'm not sure I mean, I understand the difficulty in AI and interpretability, but I'm not sure there's an alternative. It seems to me there has to be an interpretable model if you're going to be presenting it to people who aren't engineers, conservation biologists so deeply within the community.
Yeah, so I'll come back on that. It's very interesting watching, internally we have a listserv, the machine learning listserv, and it's Microsoft, so it's basically the Microsoft listserv, right? And which is great because nobody's allowed to, there was a couple catastrophes earlier on in our corporate history when everybody still had access to Microsoft All, right? And then, and so those privileges have been taken away, but kind of the machine learning listserv is that opportunity to have a Microsoft All. And one of the biggest pushbacks on this topic of model interpretability are all of the people that we've hired from the financial sector, right? Because they're saying, look, you can have an uninterpretable model all you want, but that's not going to pass. Like, that's not going to fly in the financial sector just in general, but then the regulatory side as well. So I think ultimately the way this dichotomy between hypothesis-driven versus hypothesis-free science is a false one. I think the way that science has always progressed through time is we have an observational phase, and then we have an investigative phase, and then we have an observational phase. And for me, I think we're just at one of those kind of inflection points. You know, and I think from a policy perspective, I'll go back to the point I made earlier, which is just around the more data, the better. And, you know, the more good data, the better, obviously, but just in general, when you're in a data-sparse environment, the more data, the better. The US government is a massive data collection agency in many ways. And for a long time now, there's been efforts to try to open those up, and they've been hugely positive. And they've really empowered technology companies to be able to bring value to the broader US economy and globally by bringing those data sets to a much broader suite of customers and partners. And so, you know, I'm not saying that there needs to be massive shifts. It's just continuing that trend of opening up open government data. And I mean, it's always been open, but creating, going from a lowercase to a capital O on open is a really important thing. It's something that I know the technology sector in general has consistently leaned in on, both from all kinds of data, including data. So I think that's.
I think it's a really insightful question, and I just wanted to point you to Jack Dangerman gave an opening plenary speech at the ESRI Federal User Conference, and his first half hour is about how geographic data is changing policy analysis in virtually every sector in society, whether it's defense or air traffic controllers or conservationists. So it's on YouTube. It's worth your time to check it out. But I think beyond that, in the Chesapeake, we're really fortunate because we have a 40-year history and a cultural commitment to conservation. The Chesapeake Bay program has adopted our data, our high-res data, into their model. And for every goal they have, whether it's buffers along the rivers or land conservation or whatever their goal is, our data is now helping them to direct their policies and efforts. And the Bay program is not just federal, it's state, it's local, it's nonprofit. It's really quite a complex and advanced partnership, landscape scale partnership. So you will see, I think, our data influence policy over the very short term, and we're fortunate. There is a gap, though, between the users of the data and the data itself, because this is 900 times higher resolution than anything they've ever had before. And so the models they've been using to analyze data don't necessarily match up with this high-res stuff. And so there's going to be a time period of integration where the market and the data match up.
Right. So maybe one quick comment, because I want everybody to have a chance to go see the Innovation Center and the demonstrations and so forth. So.
Yeah, so just two very short thoughts. One is, any chance that we have to actually save taxpayers money, because we can increase the scale and leverage of what we're doing for the same price of what we're doing it before, which AI and computer vision and these additional tools allow us to do. That's a huge advantage. But there's a second question about risk, right? We always look at these technologies, these approaches at risk, but we fail to consider the opposite question. how much more risky it is to continue to do the same thing and expect a different result.
Right.
And I think that question never gets asked enough in terms of how many more lives could we actually have saved? How many more species can we protect because of these technologies?
Great, thanks. So I think with that, we'll end the open question forum section, and I think we can all go into the Innovation Center where there'll be some demonstrations. Is there?
Yeah, I mean, if you have time, we have well, we'll all be standing around for deeper kind of in-person questions. That's the other part of my job, is just standing around, really. No, but we've got Joel will be able to show, and some of his folks will be able to show the actual process and the maps that they produced, and be able to talk in more depth about the policies that they're working on. Sam's gonna have some stuff out there that can walk you through what they've been doing with the Kaggle competition and some of the results that they've been getting back and how some of those algorithms work. And Tanya will be showing some of the wild book examples, so you can actually name your own. What were they? Tilly the turtle, and you had a beautiful flow through. I thought you were gonna go from A to from aardvark to zebra.
Yes.
But anyway, so that is just out there in the lobby. So feel free to come by, have deeper conversations with us, and we'd love to chat more with you.
Yeah, and we want to thank you all for coming, and all the panelists here. So maybe a little round of applause.
Thanks for moderating.
Yeah, I do. Oh, man, I love what you have to say.
Well, I'd love to see how we can take what you guys have done and apply it to Madagascar. So
Sounds great. Do you know Stuart Pym?
Lucas's former advisor, and I